One of the most hotly contested procedures during the Apollo missions was how NASA dealt with the issue of the Van Allen belts, the naturally occurring belts of radiation that surround the Earth, both on the journey to the Moon and also returning from it. To some, this just proves the point that NASA never went to the Moon, because they contest that if a crew went through the Van Allen belts, they would have received a lethal dose of radiation and died during or shortly afterwards. But as we know, that didn't happen. So how did they achieve this? Mention the word radiation and most people will think of X-rays, the atom bomb, Hiroshima, Chernobyl, and therefore associate it with bad things. Yes, you do need thick lead shielding to protect against high-intensity X-rays.
In the 100 years since we discovered radioactivity, we've learned a lot about the negative effects of radiation on the human body. Thankfully, here on Earth, we're pretty well protected. We have an atmosphere 300 miles high, which has a thickness density equivalent of 7 feet.
But the radiation in the Van Allen belts is not X-rays.
You don't know what you're talking about, do you?
Because an advanced instrument called the Soft X-ray Spectrometer returned early results that will be studied for years to come. Developed and built by Goddard scientists working closely with colleagues from several institutions in Japan, Hitomi's Soft X-ray Spectrometer proved its ability to separate X-ray colors with unprecedented detail. Astronomers typically learn about the composition, temperature, and motions of cosmic sources by spreading light into a rainbow-like spectrum. Hitomi's Soft X-ray Spectrometer works differently. It used a microcalorimeter to measure the minute amount of heat delivered when individual X-ray photons struck its 35-pixel detector array. The results are simply amazing.
The problem is not only the quantity that you get more radiation, the problem is the quality. It's different radiation. We know radiation on Earth. We know X-rays, gamma rays, beta rays, we all know. But radiation in space is heavy ions, iron, these exotic particles, very heavy, very densely ionizing. We say this is a beautiful image that you see. What you see here, this one is a human cell. This is a human nucleus, so, you know, it's 10 microns approximately. And these two lines that you see here are two iron ions that you don't find in space. I'm sorry, that you find in space, but not on Earth, except in Darmstadt, the GSI, where we have it, going through the cells and making damage to the DNA. What do we know about this radiation? We really don't know much, because we don't know it on Earth. We only know it in space, or if you are exposed to the GSI by accident, which never
There are
happened.
two main types of radiation. The first is electromagnetic waves. This covers everything from radio waves through microwaves, infrared, which we feel as heat, visible light, on through ultraviolet light, onto X-rays to gamma rays. That is the electromagnetic spectrum. The second type of radiation is charged particles. These are the component parts of atoms, such as protons, neutrons, and electrons, which have been broken apart by nuclear reactions or extreme heat in the sun. These particles flow out from the sun as the solar wind, and because they have a positive or negative electric charge, they react with the Earth's magnetic field. Some are attracted to the north and south poles, where they enter the atmosphere and react with the air to create the northern and southern lights. Others are captured into the bands of the magnetic fields around the Earth, where they form the Van Allen belts. These consist of an inner and outer belt and a temporary third belt, which appears when the sun has large solar flares. These bands extend from between 1,000 and 60,000 miles above the Earth's surface, with the most active areas centered around the equatorial area of the Earth, but thin out nearer the poles. This type of charged particle radiation is also known as ionizing radiation, which means that it has enough energy to knock electrons from atoms or molecules that make up the spacecraft and the crew inside, which can cause tissue damage if there is a high enough exposure for long enough. The main types of ionizing particles in the Van Allen belts are high-energy protons and electrons. The protons can be stopped by light materials such as the aluminium skin of the craft and also the epoxy resin heat shield. Electrons, which are also known as beta particles, can penetrate several inches into living tissue, but because they're very small, they don't tend to do much damage.
Image that you see, what you see here, this one is a human cell. This is a human nucleus, so you know it's 10 microns approximately, and these two lines that you see here are two iron ions that you don't find in space. I'm sorry, that you find in space but not on Earth, except in Darmstadt, the GSI, where we have it, going through the cells and making damage to the DNA.
They can also be blocked by materials like polyethylene, which contain a lot of hydrogen. The hydrogen atoms are very light and absorb the beta particles, as well as the fibrous insulation material that was fitted between the inner and outer hulls of the command module, which would also have been a good shield against them. One problem is that when beta particles interact with large atoms like lead, they give off secondary X-rays, and this is called the Bremsstrahlung effect. So the thick lead shielding that some people think is needed to protect the crew against X-rays would ironically make the problem worse by creating more X-rays, whereas the lighter metals like the stainless steel and the aluminium of command module would create less X-rays, and even then some of the X-rays would be absorbed by the inner hull.
You can think of active shielding. You can think of electrostatic shielding. I mean, some kind of electrostatic spheres that protect the astronauts. Or even better, you can think to this thing. This is shielding. This is something I think all of you know. This is a beautiful aurora borealis. What is this? This is the shielding of the Earth, the magnetic shielding of the Earth. The solar wind with these protons and heavy ions is coming to the Earth, is trying to enter in the Earth, but the magnetic field of the Earth is deflecting these particles. They go to the poles, and then they hit the atmosphere, and you see these beautiful colors. Beautiful. There are many people going there only to see them. You see that the green colors is the oxygen. Sometimes it's more on the red than is nitrogen. So that's how Earth is protecting life, using a magnetic field. So we could think about using the same system. It's not so easy, but it can be done. So what do we do really at GSI? We simulate the cosmic rays. This is this is our accelerator at GSI. We also have many people, 1,000 people working there. We also have lawyers too. It's not scientists, but also lawyers, mostly scientists. And we can simulate the particle. We need these huge accelerators because the cosmic rays are so energetic. They are so fast. So you need a very large and expensive accelerator to simulate space radiation. But there is a nice part of the story. I told you these particles are so effective. You do remember the little astronauts killed by the cosmic radiation, which is bad if you are in space. But if you are a patient, and if you can take the same particles and you can shoot them in the tumor, not whole body, but only in the tumor, then you can cure cancer. Well, this is done. And not very far away from here. It was done in Darmstadt for many years. Now it's done in Heidelberg. This is a picture of a treatment room in Heidelberg. But they are treating the patients using heavy ions, using carbon ions in this case. So I think this is really fascinating, is the possibility that space research and medicine help each other, you know, that the same radiation which is a problem in space can be a cure for cancer on Earth. So at the end, shall we go to Mars or not? Well, I think I was supposed to give ideas here. It looks like, I mean, radiation is a problem. This is clear. Shielding, passive shielding can be a solution on the planet, but not really on transit. Maybe the best solution, the best idea is to use a magnetic shielding, is to build magnetic fields for the spacecrafts that can do what is done on Earth. So it's not really a new idea. It's the same idea that God had a few billions of years ago when he said, okay, I want to make life, but I created radiation already. What can I do now? Okay, maybe I can make a magnetic field, you know? And you see, it's very effective in protecting the Earth and our life from space radiation. Thank you very much.
So whilst we can shield against the radiation to a degree, providing it's not too strong, there are other things that the NASA engineers and the mission planners knew about. And one of these was where the thickest and most lethal parts of the Van Allen belts were, and also how the human body reacts to radiation. The effects of radiation are cumulative, which means the longer you're exposed to it, the more damage it causes. Within reason, a short exposure to higher levels of radiation is better tolerated by the body, as it has time to repair the damage afterwards. Long exposures to low levels of radiation cause more problems because the body has to try and repair itself and contend with the continual damage whilst it's doing this. If you spent an extended period within the Van Allen belts, then the effects would be lethal, but the Apollo crews only spent about 6 hours in total. Around 3.5 hours going and 2.5 hours returning several days later, effectively 2 short bursts separated by a rest period. More importantly, the course which each of the Apollo craft took avoided the most lethal parts of the inner belts completely, and they only went through the thinnest parts of the outer belt. All the astronauts wore dosimeters to measure their personal radiation exposure levels during the flight and reported results back to NASA at regular intervals. In total, the amount of radiation that the Apollo crews received during their flights to and from the moon from high-energy protons, electrons and X-rays from the Bremsstrahlung effect was much less than that of the yearly allowed dose for someone working in the nuclear industry and regularly dealing with radioactive materials. In the end, the simple answer to why the Van Allen radiation belts were not the killer issue that some people think it was, and how the Apollo missions cut the radiation exposure for the crews to between just 1 and 5% of what it could have been, is because the Apollo missions didn't need to go straight through the Van Allen belts. They basically flew around the most deadly areas and were not in the less dangerous areas for long enough for it to be a showstopper. This remains true today as it is for any future missions. Why go through it when you can just go around it? Thanks for watching, and I hope you found it interesting and informative. If you did, let me know in the comments below, and as always, please subscribe, rate and share. We also have other videos that you may find interesting on the Click More Videos link above, now showing. So it's goodbye from me, and I hope you drop by again soon.
California, and I was wondering, maybe to both of you, what are some of the challenges that you see coming up in spacesuit design, especially as we think about going to Mars and maybe on to some of the moons, like increasingly hostile environments in space, and dealing with problems of ionizing radiation to astronauts over long periods of time. So I'm just interested in what your thoughts are in that direction.
It's a good preview question for, I think, what we're going to hear about, but go ahead.
Yeah, go ahead. You can go first, I'll go second.
Well, as I had said, the first thing you do is you have to look at the mission. The jump from Gemini to Apollo is very important because the astronauts had to walk. Now with the ISS, the astronauts don't have to walk, so the lower half of the suits are not very mobile. So everything goes to mission. As far as radiation is concerned, that is a concern, and I think David is probably better trained to answer that.
Low weight suits, very low mass, very mobile. That's where the future, we think, of design and development. Radiation is maybe the #1 showstopper to keep our astronauts healthy and well. Don't think it makes sense to incorporate that into the suit design. Makes sense to incorporate that into your shelters and things like that, because you need a very high dense, high massive protection of the radiation. So I kind of decouple the two, thinking about the suit and life support system design, and then your habitat and rover design, which are better equipped to do the radiation protection.